30 minutes, 40 minutes, just talking about, I've mentioned VDI and RDS workloads, but I guess CPU utilization in general. Everything we do every single day to do with computers all generates CPU usage. So just going to talk about what actually that is and how Windows deals with it, looking at different parts of the kernel, the scheduler, so you can actually get an understanding of how all your applications work and seem to run. So again, just a little bit about me. For those that don't know me, I'm sort of the CTO at ThinScale. I've been around doing this stuff. I updated this figure recently, getting rather scary. About 15 years now. I actually first got into kind of the SBC technologies back in the Intrigue days. Has anyone heard of Intrigue? So yeah, I was delivering X11 remote windows to cab workstations back at Jaguar Cars in the day, back on 3.1. And I think Citrix actually bought Intrigue from Insignia Solutions, which ultimately became WinFrame and MetaFrame and then everything else that we now know. So I've been through all of those, did a lot of work in remote access as well, delivering F5 stuff, SCADA stuff, custom web portals, because I've always had kind of this programming background as well. Started way before just playing around with BASIC on what was an Icon Electron or a BBC. So yeah. So what are we going to cover? So what is CPU utilization? We all use CPUs. We know they consume resource, but what actually is it? I'm going to give a slightly different slant on actually what CPU utilization is and how to think about it. To say we're then going to dive inside the Windows scheduler. So we all know we've got lots of processes that are running, but how does Windows make all those processes look like they're running at the same time? So we're going to look at parts of the scheduler, so quantums, priorities, priority boosting, thread states. So this isn't everything. You could spend a full day talking about the scheduler. There's lots involved. These are kind of the key bits that I do want to cover off. The scheduling aspect of that, so taking all of these variables and applying them to algorithms to make it look like your applications are running. Dynamic fair share, I want to cover off as well. So we all know dynamic fair share prevents single users on multi-user servers from consuming all of your resource, and it actually does a very, very good job. And hopefully, if the demos work, I can actually show you it in action. Last of all, affinity. So this affinity is a stance that we take with our ThreadLocker product. I'm not going to talk a lot about that. I'm going to cover it off, but I do want to cover off affinity and how that differs from the traditional priority changing of applications that people do. So once we've got an understanding of all of that, we'll actually look at, is this a problem for me? So do I have problems with CPU utilization? When is it a problem? When is it not a problem? What to look for? Does adding a hypervisor change any of it? So if I'm talking about Windows running on some hardware, some CPUs, if I stick a hypervisor in between that and have lots of those schedulers running, how does that affect the CPU and performance on the box? We'll have a look at that. And I/O as well. I wanted to cover up, there's, even through the conference this week, there's obviously lots to talk about I/O. They tend to be the two bottlenecks. If you've got I/O problems, you haven't got CPU problems. If you haven't got I/O problems, you've got CPU problems. But I'm just going to have a look and show how I/O can actually have quite dramatic impacts on CPU utilization, depending on what you've got in your environment. A brief overview of ThreadLocker, once I've got that in, so it's very applicable to a lot of the stuff I'm talking about here. And then finally, I'm just going to prove some of this theory. So different thoughts. I was going to jump through and do demos, jump in and out of the presentation, but I've decided I'm just going to keep all the demos till the end. So I'll just run through several slides talking about it, and then I'll just put some demos and try and show you some of what I've been talking about. So, jump straight in. What is CPU utilization? I wasn't sure, so I googled it. CPU usage refers to the amount of time consumed to a process as various instructions running in a computer program. To measure CPU usage, clock ticks are utilised. Clock ticks are measured in percentage and a utilised tool for comparing time. Doesn't mean anything to anyone, right? This is CPU usage. Everybody knows it. It's the thing that everybody sees when they fire up Task Manager. If you want to know how much CPU I'm using, this is how much I'm using. And we all know, so CPUs, it's generally shown as a percentage. Wherever you see it, whether it's the task manager, whether it's your performance counters, whether it's your monitoring tools, they'll all show CPUs as a percentage. But I say my slant on this is it's actually a measurement over time. It's a very, very important distinction. So when you're thinking about CPUs, just think about you're using the CPU over a period of time rather than point in time. Because you can't use part of the CPU. You're either using it or you're not using it. You're not using half of the CPU. So when you're looking at 50%, half of your CPU is not used, you're either using it or you're not using it. So this is how I think about it. So I'm currently using 50% CPU. It's actually better phrased over the last second or period of time. I was using the CPU 50% of the time. So 50%, 75%, but 50%, you're using it, you're not using it. Very important distinction. So, as I said, you're running 50%, I'm using it 50% of the time, 50% of the time I'm wasting them, I'm not using them, they're sat idle, not doing anything. So, you take that analogy, surely this is the best outcome. So, they're at my most optimal, I'm using everything. I've got the best bang for my buck, I'm getting most out of my CPU, so most optimal performance. Right? So let me ask you this. Why do I only seem to have CPU-related performance problems when they're running at their most optimal? Hopefully I'll explain why and why that might not be the case throughout the slides. So, before we can understand why you may have problems, why you might not have problems, we need to understand how Windows deals with all of this. So we'll just delve into the scheduler. So it's part of the kernel, and basically it's responsible for making things work. It's the thing that makes all your threads, all your processes have time on the CPU. It runs everywhere. What I mean by that is you won't find a process on Windows called scheduler.exe. It's not an application. There's not even kernel threads that are dedicated to doing scheduling stuff. It runs all throughout the operating system. It's made up of a bunch of functions that you'll sometimes see referred to as the dispatcher. There's an example here. So, a very common .NET function, sleep. If you're a programmer, you send one of your applications to sleep for 5 seconds. What that's actually doing under the hood, it calls various other functions, flips into kernel mode, and a bit of scheduling code runs. What that scheduling code does is stop this thread from running and picks another one to run. So just calling a simple function like sleep invokes the scheduler. So it's all over the place. So its primary purpose is for queuing threads. Once these queued them, switching between different ones that are running on the system. That's pretty much all it does. And using all of the variables we're about to go through to work out which ones need to run. So what is a thread? Threads run your application code. That's what they do. Do we have developers in the room? Just show of hands. Great. So yeah, threads run your application code, and it doesn't have to be a C application. That could be a PowerShell script, a VB script, a batch script. Everything you do, they all come down to the minimum thing, which is a thread, and that contains your application code. We know that threads belong to a process, and a process can have many threads. You can have a collection of threads that belong to the same process in all different things. Obviously, some criteria of a process, we know that threads belonging to the same process share the same memory virtual address space. So memory allocated from one thread can be accessed by another thread in that same process. Same goes for Windows objects, such as a file. I can open a file on one thread, read it, write it in a second thread in that application. And of course, they share security boundaries as well, so same permissions apply to the different threads within those processes. Threads run for a set period of time. You don't actually have to worry about this as the developer. When you're writing your code, you don't think, I've done quite a bit, I best flip over and let somebody else have a go. It's all taken care of. It's all taken care of for you. You write your code, and it's the scheduler that stops these threads running all the time. So they do run for a set period. And of course, there's only a set number that run at any one time. So a thread runs on a CPU, and a CPU can only be running one thread at any one time. If you've got 4 CPUs in your box, you can have a maximum of 4 threads that are running at any one time. can have 3, 2, 1, you can never have more. So, quantum. So, quantum is the term given to the amount of time that a thread is allowed to run for. So typically this is 2 clock intervals, 12 on server systems. So on your client-based operating systems, the quantum is equivalent to, I'll come on to what the clock interval is, but it runs for 2 of them. There are some variations to that. So foreground processes, for example, on client operating systems get a quantum boost. So they'll run for slightly longer than everything else. That's, that just gives that responsiveness. So you want the application that's in focus, the one you're using, to have a bit more CPU time than the rest. And as I say, server systems, they're obviously not interactive, they're very much event-driven. Take a web server, it's pretty much sat there not doing anything most of the time until the request comes in. You want to give it as much time as possible to process that request, spit the answer out and go back to sleep. If you've ever wondered what this dial does, it's exactly that. So it switches between the 2 quantums and the 12 quantums that your threads can run for. Installing RDS, I think as of 2008 R2, sets this for you when you install that role. So you install server, you check its background services, you add the role, it flips it for you. If you check this on any client operating system, it will be set. It will be set to programs already. So the length of the clock interval, it can vary. Typically on the x64, x86 platforms that we're all familiar with, it's about 15 milliseconds. So it's very, very small. I had read some Linux kernels actually reduce that down to a millisecond. And I'm not sure, I need to double check with Windows 10, it may have even changed with Windows 10, but certainly 2008, 12 to Windows 7, Windows 8, it runs at about 15 milliseconds. So what does that mean? Simply, every CPU you've got in your server, it's possible for about 33 threads to run every second. Very, very, very quick. Every second. I've drawn this as 33 different threads. There's no reason why that can't be the same thread 33 times. There's nothing else that's running on the box. Priorities. I know we're probably all familiar with process priorities, the low, below normal, normal, above normal, high that you see in Task Manager. Well, actually, it's the thread that's running at the priority. Windows defines 32 different thread priorities, and the process priority is just the base. So when you have a process running at normal, it will default to 8. So all your threads will run at a thread priority of 8. But you can see they have some wiggle room. So you can call APIs to, inside your process, set the threads to run at anywhere between 6 and 10. You won't see that in Task Manager. As far as you can see in Task Manager, your process is running at normal. Actually, the threads might be running slightly higher if you've called the APIs that you need to do so. What is interesting, I'll show this in one of the demos as well, is you can see that they overlap. So one of the things that people do when they've got a process that's consuming a large amount of resource is lower its priority. So I might lower that priority to below normal, which will set all those threads to 6. But I'll show you later on that if I've got a below normal priority process that's in the foreground, I'm going to get a priority boost. So chances are my threads might run up to 8, which is actually the same level as all of the processes that are running at normal. So Task Manager is showing below normal, yes, it's running, actually the threads are running at the same priority as your normal processes. So just because it's showing below normal, then it might not be. Yeah, so real time, just to put this into perspective, we need to look at interrupts as well. So this is an x86 pattern. It defines, again, 32 interrupt levels. x64, I think it's half that. It just has less devices, but it has the same lower and upper interrupt levels. But what I was showing you here, all these 32 priorities are running down here. Okay, when you get into real time, you're running at a slightly higher IRQ. A lot of the dispatching and thread scheduling runs at a higher level. So this is all, again, this is another level of priority. So if scheduling happens, I'm up at level 2. I know that nothing at level 1 or 0 is running. That's all of my use my threads stop while the scheduler's doing its thing. When we're up into the device level, this is kind of these are your hardware devices. This is your keyboard, this is your mouse, this is your network card, your hard disk. So whenever you press a key on the keyboard, you get an interrupt and the key comes in at a really high level. It interrupts everything that's running on the machine. Processes that and then lets everything else carry on. But you kind of ask, well, if I've got performance problems, and I'm sure we've all been there, you're pressing the key and it's taking a delay for that key to appear in Word or Notepad or whatever you're doing. Why is that when you're telling me the keyboards get priority over everything else that's running? Well, it's the receiving of the keyboard keystroke gets priority, but ultimately it's got to get passed through the subsystems up to Word, and then a thread down here that Word's running has got to process that key and display it on the screen. So yes, Windows may receive the key as a priority, but actually knowing what to do with it in Word doing its processing, it's going to run at the, it'll get scheduled as per priorities that are running at. So I mentioned priority boosts, so there are more than this, but these are the key ones. So certain instances where a thread will get a priority boost, and they don't maintain them, they'll get a small boost and then they'll come back down to their level. And this is really just for making the operating system interactive. So if you've done an IL operation and it completes, you want the thread that's waiting for that to complete, you want to give it a boost so it knows it's finished and it can carry on. Same with any windowing. If you've got some windowing activity going on, you've maximised, you want that to happen straight away. You don't want a delay because some other thread's pointing to a file or something like that. So a lot of these boosts are just around making the operating system responsive to the end user. The other one is starvation. So you can get yourself into a position where you've got a higher priority process that's always running. And because of that, nothing underneath gets to run. So if you've got threads that are wanting to do work and haven't done for a while because they've not been scheduled, they'll start getting priority boosts and eventually they'll get it go on the CPU.
Would it be fair to draw the conclusion that a low priority process could use that boost to get above a higher priority process in a situation where you're maxed out?
Over time, yes. There are limits. They won't go above a certain, I forget the values, it's 15 as a priority bit. Yes, you could be in a position where you've got a low priority process. I don't know what the time period is, you're talking a long time, but eventually it will get priority over a high priority process because it's been boosted. Then it will run and then it'll start at low again. So it will run very, very slowly, but yes, it will get time on the CPU. Okay, thread states. So every thread running in the system is in a number of states. I'm going to talk about 3 of them. There are more, but they're kind of transition states. The 3 I'm going to show are the important ones. So waiting. This is the most common. If you look at so I've got 1,554 threads created on the system at the moment. 90–95% of them are in this wait state. They're not doing anything. They're waiting on an event. You've sent them to sleep. And it's a very common practice when you're creating multi-threaded applications. You typically spin up a thread and all its entire job in life is to wait for something else to happen. It's not actively doing anything. So you might look at the amount of threads you've got, but chances are 90–95% of them will be in this state from creation until that thing that they're waiting for happens. They'll do their thing and then they'll go away. So running is obviously the opposite of that. If they're not waiting, they're running. And we've already said that there's only a certain amount of these that are running at any one time. The most important state, certainly for me, when looking at performance problems, is this. Just the amount of threads that want to run, but can't because something else is running. and I'll come on to how the scheduler deals with that, and it will start to explain why you'll see certain performance problems in certain conditions. Can anyone tell me the performance counter that you can use to get this value?
Ready time?
It's processor queue length.
Oh.
You ever seen it? So the system processor queue length is the
Number of threads.
waiting. It doesn't include the ones that are running. It's just the ones that are waiting. So if you've got a high number of threads waiting, chances are you've got performance problems.
Kind of like this queue.
Yes. Yeah. So you've sent all this data down. The engine just can't process it quickly, so you've just got a backlog building up. It takes time for that backlog to be processed. Exactly the same thing here.
In ideal, that should be 0, right?
Yes. Yeah, in an ideal world, you don't have a queue. Ideally, there's just the number of threads that want to run on the number of processors that you've got. It's rarely the case. But threads typically don't run for a long time. So you may have a little bit of a queue. So they'll run, you can run 33 a second on every CPU. So,
And that's one of the counters that we're watching inside. Of course, if that goes
Yep.
up, then it's almost likely that there are some performance issues.
yes. So, how does that work in terms of the scheduling? So, Windows will implement first in, first out queue, one for every priority that your thread's going to run out. So, whenever a thread wants to run, it will go into a queue, and it will go into the end of the queue at the priority level that thread will have. And then, when scheduling actually happens, the scheduler looks down these queues and takes the first thread in the queue of the highest priority. So it's as simple as that. It looks down the queue list, finds one at the highest, takes the first one and lets it run. Scheduling those threads, as I say, happen for a number of reasons. So quantum ends. So the thread's been running for those two quantums that I mentioned. So 30 milliseconds, the thread's been running, the scheduler kicks in. What it actually does is put the thread at the end of the queue and then picks the next one to run. It might be that it's the only one in the queue, so that same thread runs again. It doesn't just run permanently, it does get scheduled, it might go out and in, but it might be the same thread that's running. You voluntarily enter a wait state. So you as a developer call the sleep function that I said, or you wait on a file to be closed, or a file handle, or a process handle. So you as a developer call one of these wait functions and your thread goes from running down to wait. At that point the scheduler picks the next one to run. The third one is preemption. So a higher priority process wants to run. So at that point, the scheduler will pick one of the running threads, put it back in the queue, and allow the higher one to run. It's an instant thing, this preemption. There are some slight differences between the way the queues work for those three. It's probably easy to depict it. I found this in one of the Windows internals books. I've modified it, but it's a really good representation of what's going on in the scheduler queues. So I haven't got all 32. I've just picked the key ones, the different process priorities. But essentially, there will be 32 of these. You've got your 4 running CPUs. I've got 4 CPUs in this server. I've got a bunch of threads that are in the ready state, so they want to run, but they can't at the moment because the CPUs are being used. And I've got a whole bunch of threads here. This would be generally lots more of these. 90-95% of your threads are in this state. So you've got, at the moment, threads 1, 2, 3, and 4 running. They're running on their own CPUs and their quantum's end. So what happens? So number 1 moves back over to the ready queue. The scheduler then decides the next thread to run. Which thread's going to run?
5.
Number 1.
Because it's
Because it's the highest priority. Yeah. So even though these guys are waiting to run, and this guy's just finished, it's going to get priority over it, because it's running a higher priority. So until these guys decide they don't want to run anymore, these guys aren't going to get a look in. Yeah, so that's just one. So you voluntarily enter a wait state. So same scenario, we've got 1, 2, 3, and 4 running at the moment. 1 calls sleep. So it goes down into the wait state. Now which one will run?
5.
Yeah, exactly. So 5 was the highest, first of the highest queue, so now 5 get to go. Preemption. There's a subtle difference with preemption, which I just want to cover off. So This is the same scenario, so 1 is still waiting down here and 5 is happily running. 1 decides it wants to run again, so it slept for the 2 seconds it was told to sleep for, and now it's woken up again. So it's ready to run. You can never be in a situation where you've got a higher priority thread waiting to run than running, so the scheduler will kick in and preempt number 5. Now the subtle difference is that 5 doesn't go to the back of the queue, it will go to the front of the queue. And the time it's spent already running on the CPU is remembered. So that could be 1 millisecond, 2, all the way up to 30. The idea of that is if it's already around for 30 of the 30 threads allowed, you don't want to give it another 30. So it stores, it goes to the front of the queue, and when it's able to run again, it will just run for that remainder. So it will run for the remaining 3 milliseconds, and then its quantum ends and it goes to the back of the queue. It's a subtle difference, but it's just in the instance of being fair to everybody else on the system. Okay, dynamic fair share scheduling. Again, as I said, this is the mechanism that prevents a single session consuming all of the resource on your box and make sure that the resources are evenly distributed across all your active sessions. Added in Server 2008 R2, I believe it's on by default. You have to turn it on. And I know it's been extended in Server 2012. I think it was disk and network as well as CPU. It was originally.
In 2008, there's a bug in the group policy, I think, that doesn't turn it off when you enable group policy. So you have to.
You have to do it by reg key or PowerShell. That's a true policy.
So as I said, its goal is to provide equal resource to all the active sessions, preventing that single session consuming all resources. It's fine if you're the only guy on the box and you've got something consuming it. You don't want to affect the other 50 users that are on the same bit of hardware. So it's baked straight into the kernel, and again, it forms part of the decision making that the scheduler does. So it just alters those parameters that the scheduler makes. So consider the same diagram. So these are now session IDs as opposed to thread IDs, and that's probably very common. Lots of different threads from lots of different session IDs, all ready to do some work. This is what it prevents. So without it, the only guys that are going to run are these guys here in session 1. These poor guys here, 4, 3, and 2. They're never going to get a look in because these guys are always running. That's obviously not what you want. So the fair share scheduling will actually take that into account when looking at priorities, and you might get an instance where this guy will get priority over this guy because it knows it's ran session 1 to have too much of that CPU resource. Okay, so affinity, I said that's this is the special mechanism which kind of breaks a lot of the rules I've just talked about. I kind of assume that every thread can run on every CPU. But affinity obviously changes that. It allows you to decide on a process or a thread level which CPUs they can actually run on. So affinity is just having that ability. So I can decide actually Word you can only run on 2 of the 4 CPUs, and any threads associated with Word will never get scheduled on these other 2. So you actually get to a position like we've got here. So this normally wouldn't be allowed because you've got a higher priority thread waiting to run. But because number 1 is not allowed to run on CPU 3, it just picks the next one. So number 5 it's okay. That's essentially what affinity settings are. So now we know how the scheduler deals with it, how resource can be consumed, different priorities, lots of different threads running quickly. Is this a problem? Is it a problem for me? How many people are panicked when they see this? Okay. How many people have been working away on their laptop and realise the fans start going? It gets hot, you open up Task Manager and you see this. But you weren't having performance problems, were you? So it can vary, is what I'm saying. Chances are you may have problems here, but there are instances where this is optimal, right? So you're not having performance problems, it's just you only notice it because your CPUs are getting hot and your fans start going on the laptop.
It also also has a lot to do with how the application is built in terms of like the main thread, right? It's responsible for the UI
Yep.
for the most part. So sometimes if it's a single threaded application or it just depends. If there's other threads in the background, maybe everything is fine. But
Absolutely,
mostly
yeah.
if there's a problem with your main thread, with your UI is not, right?
Yes, yeah, and that, you might have performance problems and have low CPU because you've got a wait event in your UI thread. Right? So actually there's nothing on the box with your application's jittering all over the place. It's just that your written application. It's nothing to do with performance problems. So my answer to it is yes, it could be. It also might not be. It is. It is a maybe. Definitely a maybe. What about these? Have I ever got performance problems if I see this in Task Manager? No, of course not. I've got plenty of room, I'm only using half of it. But I would say yes. There are scenarios where running at 50% or 75%, I can show you will have performance problems. Hopefully demos working, I can show you some of this. So again, it's another maybe. What I'm trying to say is you can't just use this alone to determine if you've got problems. You have to use other information that's available to you, like your discounters, the process queue length. It's key to combining it with this, which will determine whether you've got those performance problems or not. Okay, so an example. We'll take 50%. Remember I said you can have up to 33 threads running within that second period. So I've dotted these around, so I've got 17 of them. So roughly 50% of the time my CPU is being used. So in this pattern, I'm using 50% of the CPU. If I click my start bar, it's going to get scheduled here. So very, very quickly, and you're probably not going to notice the performance difference. What if it looked like that? So exactly the same scenario, still running at 50%. But if I click my start bar, it's going to get scheduled here. It's going to take a full half second before that gets processed. So I'll click start, it's going to wait for half a second.
Well, why doesn't the scheduler put it right after the first quantum?
Sorry?
Why doesn't the scheduler put it after the first quantum?
What, here?
Oh, is it a high priority thread?
No, so these are queued.
Okay.
So these are threads from other processes that are wanting to run. So you can't skip those if you go to the end of the queue and it runs the first one. So just a scenario where there's just a burst of activity that creates a queue. But it's just a scenario where I'm using 50%, but it's going to take half a second to process that request. And it can get worse. Imagine that scenario. Imagine a scenario on a terminal, an RDS server, all 50 users on the box click start at the same time. You're probably going to have 100 of these set in the ready queue. That might take 2-3 seconds to process, depending on how many CPUs you've got. So you don't necessarily have to be using 100% CPU. It's all to do with contention. So it's the amount of threads wanting to do work at the same time. You can only ever do 4. If you've got hundreds queuing up, you're going to be having performance problems. So does adding a hypervisor change any of this? I would say not. It just adds yet another scheduler into that mix. So simply I've got 4 processes with 4 threads, and the schedulers we've just talked about deals with making sure they run on the CPUs. If you add a hypervisor in, it's doing exactly the same thing. Instead of scheduling processes with threads, it's scheduling VMs with virtual CPUs. It's the same thing. Yes?
If I gave the VM too many CPUs, then it's going to sit there and wait until the right amount of CPUs become available, right? So in that regard, isn't it a little bit different?
No, if you only had 4 physicals but 12 virtuals, I don't think you can actually configure it that way.
Depends on the hypervisor.
Yeah.
Yeah, I mean ultimately.
But they would just get scheduled. They never run at the same time. So these are just treated as threads effectively. It is more complicated than that, but essentially a hypervisor is scheduling threads from a process or vCPUs from that from a virtual machine. It's actually got an easier job because these are defined quantities. You know how many VMs it's running, it knows how many virtual CPUs it's got. The poor Windows scheduler has no idea how many processes are going to be created and how many threads within each process. So it's got a hard job to do. And what about I/O? So does I/O impact my CPU utilization? I would say it does, but it's not as much as you think. So if we take this very basic example, this is what happens when an application writes to a file. You call a function, calls some other functions, transitions into kernel mode, IRP gets generated, goes through all your filter drivers, your antivirus, your layering, all of those stuff, through NTFS, through to the disk driver, and eventually hits the disk. All the boxes in white are CPU driven. When it gets to the disk, it just tells the disk to go and write it, gives it a memory address, it says go off and do it. Whilst the disk is doing that write, you go into a wait state. So you're not actually consuming CPU while the disk is actually writing that data. Once the disk completes, it notifies you and you get a yes or a no, I've done it, failed, whatever. If you look at that over time, it's very interesting. So all of that CPU work happens very, very quickly, and it's actually the operation of writing to the disk that takes the large amount of time. And that's why, I'll show you with a demo, depending on the disk that you're writing to, you're going to have a higher CPU profile to do the same thing.
So in that stage, the CPU queue will go down, the disk queue will go up.
Yes.
Right?
Yeah, so the CPU is told the disk to go and do something, and it just waits for the disk to notify you that I've done it. And then, obviously, while that's waiting, another thread gets going. I would talk about thread locker. I'm running short of time, so I want to get to some of these demos. So thread locker is our way, our version of controlling this excessive CPU usage. I've mentioned affinity and priority, but we mainly do it around affinity, and it's all about controlling the affinity of processes, but only when it's needed. So I've talked about the priority can have its problems. You can have below normal that runs as normal, and eventually they'll get boosts. If you look at the affinity controls, we're actually physically separating different processes to run on different CPUs, which prevent that 100% thing that we know can be bad. Okay, let's start with an I/O test. So I've got an application here, which what it's going to do, it's just writing to 4 files as quickly as it can to 4 local disks. Their files get to 200 meg in size, and then they sync to the beginning and keep going. So I'm achieving whatever megasecond. But you can see I'm not actually using hardly any CPU. So I'm writing 300 meg times 4, but I'm not consuming CPU. All of the time taken is on the disk. I'm going to just change the drive letter. This is a RAM disk. Okay? So, because I'm not, the CPUs are responsible for writing to the RAM disk, it's consuming a lot more CPU, you're not offloading off to a disk, and it can get worse. So, RAM disk is probably a bad example, but let's consider the new
storage.
Yeah, or your I/O cache driver with MCS. They all do the same thing. So just by implementing a driver like that, or a RAM disk, yes, you get massive I/O performance, but just be wary of the impact it can have on your CPU profile. Applications that were consuming not a lot might start consuming quite a bit of resource.
So keep things low intention.
Okay, this is the other one just quickly, I won't get a chance to do all of them. Loop count, it's just an application I've written, 2 threads. First one just increments a value as quickly as possible and runs forever. Then every half second another thread wakes up and displays that value. So every half a second I'm doing 17 million additions. It's quite a lot.
I wasn't written that bad.
No, it wasn't. I've also got a CPU generation tool. So I'm going to generate 3 threads that run for a second and sleep for more. Little bit of impact. I'm probably at 100% CPU there because I've got 3 threads from one guy. Yeah, just leave that one there, and 1 thread from here. So I'm running at 100% CPU. But have I got performance problems? Seems okay. Now, that burst scenario I was talking about. Well, let's just up this to 4. You can see it's now being shared, so it's doing less, but from a performance point of view, still fine. This is just an acceptable amount, and that's the problem. Well, once you get to 100%, performance, it doesn't just stop, it just slows down, and you will reach a point where that becomes unacceptable for the users. What that point is will depend on the application and the user. What is interesting is that now if I generate 128 threads.
So you're using Excel basically?
You start seeing this. So down from 19 million to 5,000. It's a massive difference. The other thing that's interesting is the thread that wakes up every half second isn't waking up every half second anymore, because it's in a queue, stuff to do. And then once you're in this position, you do start seeing. One last one. If I do 600, 400. So 128 threads running for 600 milliseconds, sleeping for 400. Okay, same thing, we're not waking up every whatever, different values, low values, not at 100%.
Yeah.
Yeah?
So it's choppy.
Yes. So I've got 128 threads that want to run for 600 milliseconds, and then they don't do anything, so I'd like to say you've got this jittery effect.
And then you get a call,
Yes.
slow.
This can actually be worse than sustained poor performance. If you get random performance, that's generally worse.
Yeah,
Basically what Access Performance Manager does. Because it pauses and causes that salt.
Yes, yeah, pause start, pause start, pause start.
So monitoring for 90% up CPU doesn't make any sense.
Yeah, you can. I mean, I can play with these numbers. I can do 505, and you can't get down to 50, but around
Yeah,
75
but
and above
yeah,
mark,
yeah.
you can have. I mean, you'd look at that and you'd think, I've got a threshold of 95, my server's fine. Actually, users are screaming at you, and as you can see.
But also here the queue is the right.
Yeah, what's the cross the queue list
Is
there?
it queue?
Yeah.
It's not under CPU for some reason.
Is that still responsive? Come on.
That's it.
Something like that, yeah. Okay, so if I put it back to 4, yeah, I think let's just run those constantly. Yeah, so you can see this increasing. So this will be showing 100%, but if I combine that 100% with this value, I probably haven't got anything to worry about. You can really good. If I then up that to the 128 value. Okay.
What does it say?
Now I've got problems. I've got 140 threads waiting to do something. You're just cycling through them. Yeah.
You got try longer, so I'll answer.
No.
Did you just deny the service yourself?
I think so. Okay, I did have a few more, but if you want to see them, please come and grab me afterwards. Just a few takeaways. So, remember, CPU it's measuring over time, and that's the key thing. Using 50%, you might only be using 50% in the first half second or the first sample. If you're sampling every 5 seconds and using 50%, you could have 100% for 2.5 of that. It's very important to understand. Scheduler gives priority adjustments, so the priority that your threads are running at might not be what you think based on what you're looking at in Task Manager. 100% CPU is not necessarily bad, or it could be bad. There are other factors, and 75% is not necessarily bad, but at the same time 75% could be bad. We've seen examples of that. There are obviously extreme examples, but it can happen. And then of course changing I/O profiles can have a big impact on your CPU. Just swapping out a disk with a RAM drive will have a big impact on CPU utilisation. That's it. Any other questions? Stuff. That's to say. Thank you.